We are in section 7.2, estimating a population mean. Remember, x bar is the point estimate of mu. We can use a z statistic to determine the probability of getting a certain sample mean. If the sample is sufficiently large, we say greater than 30. If the sample is small, then the distribution is not normally distributed for sure, and the t statistic must be used instead of a z statistic. The t distribution has more spread than the z distribution. The graph down here, you will notice that there's two different t distributions depending on the size. So one of them, n, is smaller than 30, and the second one, n, is closer to 30. And then we also have a z distribution, which is what we've been studying so far in this course. And as you notice, as that n increases, it gets more, our distribution begins to look more like our z distribution. So the t distribution is typically used to study the mean of a population rather than to study the individuals within a population. In particular, it is used in many cases when you use data to estimate the population mean. For example, using the sample mean of 20 homes to estimate the average price of a new home in California, or when you use the data to test someone's claim about the population mean. For example, is it true that the mean price of all new homes in California is $500,000? The connection between the normal distribution and the t distribution is that the t distribution is often used to analyze the mean of a population if the population has a normal distribution or fairly close to it. Its role is especially important if your data set is small or if you don't know the standard deviation of the population, which is often the case. So students' t distribution, suppose a simple random sample size n is taken from a population. If the population from which the sample is drawn follows a normal distribution, the distribution of t would equal x bar minus mu divided by the sample standard deviation divided by the square root of n, follows a t distribution with n minus 1 degrees of freedom, and x bar is our sample mean and s is our sample standard deviation. Right below this, we have some properties of the t distribution. So the t distribution is different for different degrees of freedom, which again is found by doing n minus 1. The t distribution is centered at 0 and symmetric to 0. The area under the curve is 1, and the area under the curve to the right of 0 is equal to the area under the curve and left of 0 is equal to 0.5. Number 4, as t increases or decreases without bounds, the graph approaches but never equals 0. 5 says the area in the tail of the t distribution is a little greater than the area in the tail of the standard normal distribution, and this is because that graph is a little bit more spread out. 6 says as the sample size n increases, the density curve of t gets closer to the standard normal curve that we saw up above, and this is called the law of large numbers. On the next page it says remember that z sub alpha is used to represent the z-score, whose area under the normal curve to the right of z sub alpha is alpha. So similarly, t sub alpha is used to represent the t-value whose area under the t distribution and to the right of t sub alpha is alpha. So to find the t-value with the TI-84 graphing calculator, we're going to go to second vars and go to number 4, which is inverse t. And then note that if you are given the population standard deviation, which is sigma, then we're going to use inverse norm. And in order to use inverse t, we are going to input an area to the left and the degrees of freedom, which again was n minus 1. And that was equal to our degrees of freedom. If you have a TI-83 or some of the older style 84 calculators, you won't have inverse t on your graphing calculator. So you have a few options. One is to contact and go to the T-Mark if they are open and have them install the programs onto your calculator for you. If not, you can watch a YouTube video and actually program your calculator yourself and make that program be on there. It's pretty easy. It does take a few minutes to do though. So a few options there. First example on here says determine the following in round 3 decimal places. First one says to find the t-value such that the area in the right tail is 0.02 with 19 degrees of freedom. So what we're going to do is we're going to go ahead and sketch the curve first, and then we'll use our graphing calculator to kind of help us out. So our curve, remember our t-distribution looks similar to our standard normal distribution. We have it centered at 0, but it is more spread out. This says the area in the right tail is 0.02, which is rather small. So this little shaded area here is 0.02. And in order to come up with our z value, we need to input in the area to the left. And the area to the left that we have over here is going to be 1 minus the 0.02, which is equal to 0.98. And so with our graphing calculator, we are going to go to inverse t. So our t sub 0.02. We are going to go to inverse t, and we need to input in the area to the left and also our degrees of freedom. On your calculator, we are going to go to second vars. We're going to go down to inverse t. We're going to enter in the area to the left, which is going to be 0.98, and our degrees of freedom, which are 19. And then we're going to go to paste, select enter, and we get our t value. From the calculator, we get 2.205. The second part on here says find the t value such that the area in the right tail is 0.10 with 32 degrees of freedom. So again, we'll sketch our t distribution. And again, a little bit more spread out than our standard normal and centered at 0. This time we have 0.10 in our right tail. And so that area to the left is going to be 1 minus 0.10, which is equal to 0.90. And then in order to calculate this, we are going to still use our inverse t. So t sub 0.10 is equal to, on your calculator, we're going to go to second vars down to inverse t. Area to the left is 0.90. Degrees of freedom for this problem are 32. Paste, select enter, enter again, and again we get our t value. And from the calculator, we get 1.309. Part C says to find the t value such that the area in the left of the t is going to be 0.05 with 6 degrees of freedom. So again, we're going to sketch our t distribution, which is a little bit more spread out than your standard normal, centered at 0. This time it says the area in the left is 0.05. So this is the area that we need in order to do our inverse t on our calculator. However, I want you guys to notice that the area in the right is going to be 1 minus 0.05, which is 0.95. And so when we write this in the way that the MyOpenMath will use it and the way that things will be expressed in the textbook, along with the notes, is that we have t sub 0.95 is equal to an inverse t. Again, you input that area to the left and your degrees of freedom. We're going to go second vars to inverse t. The area that we have in our left tail is 0.05, and our degrees of freedom for this problem are 6. Down to paste, select enter, and we get our t value. From the calculator, we get negative 1.943. And again, it's on the left of 0, so that makes sense that this is a negative value that we get for our t. Part D says to find the critical values that correspond to a 95% confidence, and we have 16 degrees of freedom. So again, we're going to go ahead and sketch our curve. And our t distribution is centered at 0. When we talk about 95% confidence, again, remember that 95% confidence would be in the middle. So this is going to be our 95% or 0.95 in the middle. And that means the area that's going to be left over in these little tails is going to be found by doing 1 minus 0.95 and dividing that by 2. So we get 0.05 divided by 2. Or in each of these tails, we get a little area of 0.025. So the first little t value that we have is going to be t sub, and the area to the right is what we put down for our alpha, which is going to be 0.975. Likewise, the second value we have is going to be t sub, and the area to the right is 0.025. So we're going to have to use our graphing calculator in order to calculate both t sub 0.975 and t sub 0.025. And using inverse t for both of these. To calculate both of our t values for this problem, we're going to go second vars to inverse t. For the first one that we have, the area to the left is 0.025. Degrees of freedom for this problem are 16. Paste, select enter, and we get our first t value. For our next one, we're going to go second vars down to inverse t. Area to the left on this problem is 0.975. And degrees of freedom 16. Paste, select enter, and we get our second t value. From the calculator, we get negative 2.120 for the first one and positive 2.120. I want you guys to notice that those values are identical to one another except for one is negative and one is positive. And that is again because our t distribution is symmetric. So the next thing right below this says constructing a confidence interval for a population mean with a TI-83 or 84 calculator. First step is to verify that you have a simple random sample, the population is normally distributed, or that your sample size is sufficiently large, which is going to be 30 or more. So we have step 2 is going to be stat test, and we are going to go to t interval. I want you guys to note there's a note over here that says you're going to use z interval if sigma is known. And remember, sigma is your population standard deviation. Again, that's your population standard deviation. If the data is raw, we're going to highlight data, and we're going to put our data into L1 and set the list to L1 and the frequency to 1. If summary statistics are known, we're going to highlight stats and enter in the statistics. Enter your confidence level following the C level, and then you're going to hit enter on calculate. Your answer is going to be given to you guys as the lower limit or your lower bound and your upper limit or your upper bound. And then we need to interpret our results. So the next example on the next page, we're going to go ahead and circle that, and we'll look at that one together in class. So let's look at the next example. The next example says that travelers pay taxes for flying, car rentals, and hotels. The following data represents the total travel tax for a 3-day business trip to 8 randomly selected cities, round 3 decimal places. So the first thing says to determine the point estimate for the population mean for travel tax. So in order to do this, we have raw data. We're going to have to take our raw data and input this all into L1. Remember, your point estimate for the mean is going to be x bar. And in order to get x bar, we need to use one variable statistics. So take a second to enter in all those numbers and do one var stats, and then get your value. From your calculator, rounding 3 decimal places, we get 83.349. And again, this is in money. So about $83 is about what you would spend in travel taxes. So part B says to construct and interpret a 95% confidence interval to estimate the mean tax paid for a 3-day business trip. So a few things. One, our sample is very small. So somewhere in here it should state that this is coming from a population that is going to be normally distributed. This problem does not say it. However, most of the problems for you guys' book and My Open Math will say it. And so we're going to go ahead and construct our 95% confidence interval for the mean tax paid for that 3-day business trip. And so since we do not know our population standard deviation sigma, that means that for this problem we will be using t-interval. And we also have data given to us, and all those numbers you should have already listed into L1. On your calculator, stat, edit, and you need to enter in all those values for the 3-day business trip taxes into L1. Double check your numbers to make sure they're entered in correctly. And then we are going to go to stat, to test, and to our t-interval. We are dealing with data here. We are not dealing with stats, which are asking for actual values. Since we have our data, all of our data is entered in L1. Frequency is set to 1. And for this problem, our confidence is going to be set at 0.95. We have a 95% confidence interval. Go down to calculate, select enter, and you are going to get your value for your lower bound and your upper bound. And also notice that you also have your x bar, which was your point estimate for this problem. So from the calculator, we get a lower bound of 73.046 and an upper bound of 93.652. Another way to write this is going to be that our mean, population mean, is going to be somewhere between $73 and about 5 cents and $93.652. Again, different ways to write your answer that we discussed earlier. And so it also does say to interpret. And so when we interpret, we need to discuss this. And so we're going to say about 95% of these confidence intervals contain the true population mean travel tax. And about 5% will not. So part C says, would you recommend to a researcher who wants to increase the precision of the interval but does not have access to any additional data, what they can do? And what they can do is decrease the level of confidence. So decrease the level of confidence. And this will allow them to increase the precision. Right below this, there's another box to give a star to. And this says, determining the sample size of n. And back in section 7.1, we also saw how to find the sample size for n when you had a prior estimate and when we did not have a prior estimate and we're dealing with proportions. This is determining the sample size of n when we're dealing with a mean. So it says required sample size to estimate the population mean, mu, is given by n equals, we have z alpha over 2 times sigma, which is our population standard deviation, divided by e, which is our margin of error, and then that whole quantity is going to be squared. Remember what z alpha over 2 is? That is listed in these notes. If you go back to page 2. So again, on page 2, we have a table here that gives us the values of z alpha over 2. And we also had an example right below this that showed us how to calculate our z alpha over 2 if we do not have 90%, 95%, or 99% confidence. The other equation that we have listed in our box is for E, which we saw earlier in the previous section, which is going to be our upper bound minus our lower bound divided by 2. It also says where n is going to be rounded up to the nearest whole number, and that's for that previous equation in the box. So what could be done to increase the precision of the confidence interval? There's two things that could be done. We can increase the sample size or decrease the level of confidence. The next example we will start together and then we will finish in class. So this says, a recent Gallup poll asked Americans to disclose the number of books they read during the previous year. Initial survey results indicate that sigma is equal to 16.6 books. So that's our population standard deviation. Part A says, how many subjects are needed to estimate the number of books Americans read the previous year within 4 books with a 95% confidence. So 95% confidence, we want this to be estimated within 4 books, and we're asking about how many subjects. So it's asking us for how many subjects, is asking us to find n. And the number of books, we're talking about the mean number of books that you would read. So this is going to be a mean problem. We also have within 4 books. That within 4 books is our margin of error. And 95% confidence is our confidence level. So I'm going to go ahead and look at the formula that was at the bottom of the previous page, and I'm going to go ahead and copy that formula down. We have z alpha over 2 times sigma divided by e, all squared. And for 95% confidence, we need to go back on page 2 and look at the table. And that value that we have is 1.960. Sigma, which is listed up above, is 16.6. And our margin of error, E, is going to be 4. So substitute this all into your calculator and calculate this. And when you do, you get 16.16. But remember, we always round up. And so this is going to work out to being 67 people. So there's 2 more parts to this. And so I'm going to go ahead and circle both of these, and we will work these out together in class. If you would like to try them on your own and see if you can get an answer, and then we can check them together in class too, that's another possibility. But definitely something that we'll explore a little bit more in class together.